Right now, as you listen to this, there is a microscopic killer hunting about 20 miles above your head.
Yeah, it is terrifying.
Right, and it's not alive or anything, but it operates with this really terrifying mechanical efficiency. I mean, a single atom of chlorine, which was likely released from, some old refrigerator decades ago, is currently shattering hundreds of thousands of oxygen molecules in the upper atmosphere.
Exactly. It is systematically dismantling the only shield keeping the surface of the Earth from just being completely sterilized by the sun.
And we just go about our days complaining about the weather or like the smog, completely oblivious to this churning ocean of invisible chemical battles happening right above our heads.
Yeah.
Battles that actually dictate the survival of absolutely everything on
No,
Earth.
the sky is not just empty space. I think that's the biggest misconception. It is a highly structured, dynamic, and, well, an incredibly fragile architectural system. Yeah. And the sources we are looking at today for this deep dive, these specific scientific textbook excerpts, they really pull back the curtain on that invisibility. We're going to examine the actual chemical equations, the structural diagrams of the atmospheric layers, and, the brutal mathematics of pollution to basically understand the mechanics of our own survival.
Okay, let's unpack this. Because to you, the listener, looking at a stack of chemical equations like O2 plus O becoming O3 or a CFC molecule breaking down under ultraviolet light, I mean, it can feel like trying to read a completely foreign language.
Oh, absolutely. It's dense.
It is.
Yeah.
So our mission today is to translate that. We want you to understand not just that the sky is up there, but exactly how it functions as a highly specialized radiation shield. And probably more importantly, how our human conveniences have inadvertently triggered these massive chain reactions that are altering the planet.
Right. We need to trace the line from, say, a mundane appliance in a suburban kitchen all the way up to the edge of space, and then watch how the chemical consequences just rain right back down on us.
It's all connected.
Exactly.
Yeah.
And to do that, we first have to map out the physical architecture of the atmosphere. We need to identify our exact location within it. So the text lays out a very clear four-tier structure, and it starts right where we live, which is the troposphere.
That's the ground floor.
Right.
And the text says it extends from the Earth's surface up to about 12 kilometers.
Which is, it's an incredibly thin veneer when you actually consider the size of the Earth.
Right.
Like if you were pointing a car straight up and driving at highway speeds, you'd drive out of the troposphere in just a few minutes.
Wow, really? Just a few minutes.
Yeah. But this thin layer is where essentially all of our weather happens. It's where all the clouds exist and where the vast majority of the atmospheric mass is just concentrated. It's the densest layer packed with all the gases we breathe.
And as you move up through that layer, it gets colder. I mean, anyone who's ever climbed a mountain or, flown in a commercial jet knows that.
Sure, it's basic intuition.
Right. But the text explicitly states that once you cross that 12-kilometer line and enter the next layer, which is the stratosphere, extending up to 50 kilometers, the temperature rule actually flips. It gets hotter the higher you go. Which feels wrong, right? It violates everything I instinctively know about moving away from the warm surface of the Earth. Like, why is it getting hotter?
So that temperature inversion is the defining characteristic of the stratosphere. And it happens strictly because of the ozone layer. Unlike the troposphere, which is basically heated from the bottom up by the Earth radiating warmth, the stratosphere is heated from the top down.
Okay, so the heat is coming directly from the sun.
Exactly. Ozone molecules are up there actively absorbing highly energetic, lethal ultraviolet radiation from the sun. When a molecule absorbs that intense radiation, it physically vibrates, and that kinetic energy just manifests as heat.
So it's basically absorbing solar bullets and converting that kinetic energy into thermal energy.
Precisely. And this creates a very specific physical environment. Because, warm air naturally wants to rise and cold air wants to sink. Having the warmer air on top means the stratosphere is incredibly stable.
There's no mixing.
Right. There's almost no vertical mixing. It is literally stratified, which is where the name comes from.
Okay, think of the atmosphere like a high-security skyscraper. Yeah. The troposphere, that bottom 12 kilometers we talked about, is the bustling lobby.
I like that.
It is completely chaotic. People are running in and out. The wind is blowing. It's raining. Weather systems are just colliding into each other. Human daily life is happening in all its messy glory down there.
Chaos.
Total chaos. But then you take the elevator up to the stratosphere. You step out, and it is the secure, temperature-controlled server room. It is eerily quiet. It is stable. And it's where the most vital protective software for the entire building is just running silently in the background.
That is a perfect way to visualize it.
Eh.
The weather and the turbulence stay trapped down in the lobby. The server room is dedicated entirely to radiation defense.
Right.
And as we continue our mental elevator ride up, the architecture gets even more extreme. Because above the stratosphere, from 50 to 85 kilometers, is the mesosphere.
Okay.
And without the ozone layer there to absorb UV heat, the temperature plummets dramatically, making it actually the coldest place on Earth.
Wow.
And finally, from 85 up to about 120 kilometers, we hit the thermosphere.
120 kilometers. I mean, if the Earth were an apple, this entire 4-story architectural structure we just mapped out would be vastly thinner than the skin of that apple.
It really puts it in perspective.
It is a terrifyingly finite resource.
Yeah.
And the chemical mixture that fills this thin envelope is incredibly specific. The source gives us the baseline composition of the lower atmosphere, and it's 78% nitrogen, 21% oxygen, 0.93% argon, and 0.03% carbon dioxide.
Right, so nitrogen takes the overwhelming majority. We tend to focus entirely on oxygen because our biology demands it, but we are primarily swimming in a sea of nitrogen.
Which feels almost like filler. Like, what is the evolutionary or chemical purpose of having 78% nitrogen? Why not, more oxygen?
Well, if oxygen were at much higher concentrations, say 30 or 40%, the planet would literally be a tinderbox.
Oh, because it's flammable.
Exactly. Oxygen is highly reactive. At those levels, a single lightning strike could cause damp vegetation to just spontaneously combust.
That sounds like a nightmare.
It would be. Global firestorms would ravage the surface. So nitrogen is largely inert. It acts as this massive chemical buffer, diluting the oxygen to the exact sweet spot of 21%.
Right, so it's enough to keep us breathing, but not enough to burn us alive.
Precisely. It is enough to support complex, high-energy metabolic life forms like humans, but not so much that the biosphere just burns to a crisp.
It's a very delicately balanced recipe. You have your 78% buffer, your 21% life fuel, and then these tiny fractions of argon and carbon dioxide.
Yeah.
And we'll definitely be coming back to that 0.03% carbon dioxide later, because as tiny as that number is, its molecular structure allows it to punch way above its weight class.
Oh, it really does.
But for now, I want to take the elevator back down to the stratosphere. I want to look at the servers running in that quiet room, because the text tells us the maximum concentration of ozone lies in a really tight band about 25 to 30 kilometers above our heads.
This is where the chemistry in our source material becomes a literal story of survival. The text defines ozone as an allotropic form of oxygen.
Okay, allotropic.
Yeah, it basically means it consists of 3 oxygen atoms bonded together, which is denoted as O3. This is fundamentally different from the oxygen we breathe down in the lobby, which is O2, a diatomic molecule of just 2 oxygen atoms.
So allotropic, that means it's the exact same fundamental element, just arranged in a different geometry, right? Like how, say, a lump of coal and a diamond are both just pure carbon, but the structural arrangement changes everything about how they interact with the world.
That is exactly it. The physical and chemical properties change completely based on that geometry. O2 is stable. Our lungs actually evolved to use it for cellular respiration. But O3, ozone, is actually a toxic pollutant if you breathe it in high concentrations down here in the troposphere. It severely damages lung tissue. But up in the stratosphere, its specific molecular geometry is the only thing that absorbs the sun's lethal UV radiation.
The source text is very blunt about this. It just states, otherwise ultraviolet radiations would cause skin cancer. It sets up ozone as a literal physical shield. But how does it even get there? The Earth doesn't just have this fixed permanent supply of ozone that was manufactured at the dawn of time, does it?
No, not at all. It is a highly active, perpetual engine of creation and destruction. What's fascinating here is the dynamic equilibrium of this system. The text explains that ozone is formed naturally in the atmosphere by the association of an oxygen atom with an oxygen molecule.
So it's constantly being made.
Yes. Under normal atmospheric conditions, the concentration of ozone remains remarkably constant through this continuous loop of atmospheric reactions.
Let's break down the actual mechanics of that loop. Because the source provides the formation equation first, which is O2 plus O becomes O3. So you have a standard oxygen molecule combining with a free oxygen atom. But where does a lone solitary oxygen atom come from in the first place? I thought you said oxygen always preferred to travel in pairs.
It definitely does, but the extreme energy of the sun forces them apart. High-energy UV radiation from the sun strikes the regular O2 molecules in the upper atmosphere.
Okay.
The photon's energy is absorbed by the covalent bond holding those two oxygen atoms together. And that energy is so intense that it physically snaps the bond. The O2 molecule is just split into two individual, highly reactive oxygen atoms.
So the sun provides the weapon that shatters the oxygen.
Exactly. And those solitary shattered atoms then drop down slightly in altitude, bump into intact O2 molecules, and lash on, forming O3. So the sun's energy literally forces the creation of the shield that blocks the sun's energy.
That is beautifully elegant.
It is.
But it's only half the loop, right?
Right. The second part is decomposition. The newly formed ozone, that O3, also interacts with incoming UV light or with other free oxygen atoms floating around. The source gives the decomposition reaction too. O3 plus O becomes two molecules of O2.
Ah, okay.
So an ozone molecule encounters a free oxygen atom, and they just rearrange themselves back into two regular, stable oxygen molecules.
So the shield is constantly being broken down and rebuilt molecule by molecule every single second of the day. The rate of formation perfectly matches the rate of destruction, which keeps the overall thickness of the ozone layer stable.
That is the textbook definition of dynamic equilibrium.
Yeah.
It is this microscopic chemical balancing act happening 30 kilometers in the sky, absorbing lethal energy through the literal physical breaking and making of atomic bonds.
It just marvels me how fragile this is. Like, the only thing standing between us and total sterilization is a single extra oxygen atom tacked onto the air we breathe. Without that third atom, without O3, the biological consequences would just be apocalyptic. And for millions of years, that self-healing loop, formation, decomposition, it just kept humming along. The Earth was safe.
Safe. Until human beings decided they wanted colder beer and air-conditioned living rooms.
Right. Enter the saboteurs.
Exactly.
Yeah.
We introduced chlorofluorocarbons, or CFCs. The source text identifies these explicitly as the primary cause of ozone depletion. These synthetic compounds were engineered to be refrigerants and propellants, and honestly, from a mid-20th century engineering standpoint, they were considered miracle chemicals.
Because down here in the troposphere, down in the lobby, they are basically invincible, right?
They are incredibly chemically stable. They are non-toxic, non-flammable, and highly unreactive. I mean, you could have a refrigerator full of CFCs leak into your kitchen, and it wouldn't poison you, it wouldn't catch fire, it would just harmlessly dissipate. They're perfectly safe for the lobby.
But the text notes exactly what happens next. It says, these compounds leak in one way or other, escape and diffuse to stratosphere. Because they are so stable down here, they don't get broken down by rain or normal weather systems, do they? They just slowly, inevitably drift upward.
They drift for years. They just keep floating up until they finally cross into the stratosphere, reaching that 25-kilometer mark. And here, the environment is fundamentally different. The text explains the specific chemical trigger. Ultraviolet radiations break the carbon-chlorine bond in CFCl3.
Wait, hold on. Let me look at this equation. CFCl3, that's 1 carbon, 1 fluorine, and 3 chlorines. I thought you just said these molecules were incredibly stable. Why is the chlorine suddenly getting ripped apart just because it got high enough in the sky?
Because of the raw power of unfiltered ultraviolet radiation. Down in the troposphere, we are shielded from the most intense UV light by the ozone layer itself. But once the CFC drifts above or into the ozone layer, it is exposed to the full, unmitigated force of the sun. The specific frequency of that intense UV light perfectly matches the resonant frequency of the bond holding the chlorine atom to the carbon atom.
Oh, wow.
Yeah, so it absorbs the photon, the bond vibrates violently, and it just snaps. The molecule fractures.
And the source provides the exact equation for this fracture. It says CFCl3 under UV light becomes CFCl2 plus Cl with a little dot next to it. What exactly is that dot?
That dot is the symbol of a free radical. And to understand why a free radical is so dangerous, we have to look briefly at the quantum mechanics of atoms.
Okay, lay it on me.
Electrons naturally seek to exist in pairs. It is their lowest, most stable energy state. So a free radical is an atom or a molecule that has an unpaired electron. It has been violently stripped of its partner.
So an atom with an unpaired electron is basically fundamentally unbalanced.
It is chemically desperate. It is highly reactive and unstable. It operates like a frantic game of molecular musical chairs. The chlorine radical violently seeks an electron to steal from another molecule just to stabilize itself.
Yeah.
And up in the stratosphere, this desperate chlorine atom finds a very abundant target. the ozone molecule.
It attacks the O3.
Yes.
The text lays out the equation for this attack. O3 plus the chlorine radical becomes O2 plus OCl with a dot.
Right. So the chlorine radical crashes into the ozone, rips one of the oxygen atoms away to seal its electron, and leaves behind a standard, stable O2 molecule.
So the ozone is completely destroyed.
The shield is broken, exactly. And the chlorine has temporarily stabilized itself by bonding with the stolen oxygen, forming an oxygen-chlorine radical, which is that OCl.
But the reaction doesn't start there, does it? Because this is where the textbook describes what is essentially a horrifying chain reaction.
It is a chain reaction. Remember, in the natural ozone cycle, there are solitary free oxygen atoms floating around waiting to build new ozone. Well, the text shows us what happens when that OCl radical meets one of these free oxygen atoms.
Okay.
The equation is OCl radical plus a free oxygen atom becomes O2 plus the chlorine radical.
Wait, so the free oxygen atom rips the oxygen away from the chlorine to form a nice stable pair O2, and in doing so, it just kicks the chlorine radical back out on its own.
Exactly. The chlorine radical emerges completely chemically intact, re-energized, and totally unbalanced again. It was not consumed by the destruction of the ozone. It just facilitated the murder and stepped away, ready to hunt its next target. It acts as a perfect chemical catalyst.
Here's where it gets really terrifying. The free radical is it's like a desperate thief running through a crowded room. It violently steals a purse from someone, which is breaking the ozone molecule, but immediately someone else steals the purse from the thief, leaving the thief desperate and empty-handed again, so they immediately attack the next person, over and over and over.
That is a brilliant analogy. And that mechanism of molecular theft is exactly why a single chlorine-free radical, released by the decomposition of a CFC molecule, is capable of immense, disproportionate destruction. The source text puts it plainly, stating, a single chlorine-free radical released by the decomposition of CFCs is capable of destroying up to many lakhs of ozone molecules.
Many lakhs. Just so we're clear on the math, a lakh is 100,000. So we're talking about hundreds of thousands of ozone molecules destroyed by a single chlorine atom before it eventually drifts back down to the lower atmosphere or, gets neutralized by a rare terminating reaction. One atom from your old air conditioner dismantling hundreds of thousands of protective shields.
And keep in mind, humanity was releasing millions of tons of CFCs into the atmosphere every single year for decades. The mathematics of the destruction were just overwhelming. The natural equilibrium, that beautiful self-healing loop of formation and decomposition we talked about earlier, was completely overrun. We were artificially accelerating the rate of decomposition by orders of magnitude, while the rate of formation remained bottlenecked by the sun.
Right, because you can't withdraw $10,000 a day from a bank account that only deposits $10 a day without catastrophic collapse.
Exactly.
And our atmospheric bank account went deep into the red. The text notes that the region in which ozone layer depletes is called ozone hole, and it really didn't take long to find it. The source says, signs of ozone depletion were first noticed over Antarctica in 1980s.
That discovery was a massive shock to the global scientific community. The depletion wasn't just some slow, uniform thinning across the globe. It was a massive gaping wound localized over the pole, and it was happening much faster than any theoretical model had predicted.
And it was spreading. The source adds, since 1990s, depletion has also been recorded over the Arctic as well. So both poles were opening up like giant skylights, allowing unfiltered lethal solar radiation to just pour straight into the lower atmosphere.
Right.
Which brings us to the physical consequences cascading all the way back down through the skyscraper. A hole in the sky above Antarctica doesn't just stay in the sky.
No, because the Earth's systems are inextricably linked. The source outlines several distinct, severe consequences. The first and most direct biological impact is explicitly stated. Depletion of ozone enables ultraviolet radiations of sun to reach to the Earth that can cause skin cancer to human beings and other animals.
And that makes sense. That UV radiation physically impacts our biology. It penetrates the skin and literally shatters the DNA strands inside our cells, causing them to mutate and replicate uncontrollably.
Yeah, that's the direct mechanism.
But the text goes on to list other impacts that are less obvious, but systemically far more dangerous. Point 2 states, decreased ozone layer will increase infectious diseases like malaria. Now wait, how does UV light create mosquitoes?
Right, it seems like a leap.
I understand sunburns, but how does a missing chemical shield in the stratosphere actually lead to more malaria cases on the ground?
Well, it doesn't create mosquitoes directly, but it fundamentally alters their environment. Increased UV radiation penetrating the atmosphere affects the temperature profile of the lower atmosphere and the oceans. It literally warms the microclimates.
Okay.
Furthermore, intense UV exposure is actually known to suppress the human immune system, which makes populations biologically more vulnerable to infection overall. But the primary driver here is the climate shift. As the global temperature dynamics change due to this altered energy balance, the habitable, humid zones for disease vectors like mosquitoes begin to expand geographically.
So a region that used to be, too cold in the winter for mosquito larvae to survive suddenly stays just warm enough. The vector footprint grows. A broken chemical bond in the stratosphere expands the map of infectious disease in the troposphere.
The interconnectedness only gets deeper from there. Point 3 in the text highlights that UV radiation can change the life cycle of plants, disrupting the food chain.
Ah.
Because plants are essentially biological solar panels, they are incredibly sensitive to changes in the light spectrum. Excessive UV radiation actively damages their photosynthetic machinery. It stunts their growth, alters their flowering times, and reduces their overall biomass yield.
And if you damage the foundation, the whole house sinks. I mean, if the plants are stunted, the herbivores starve. If the herbivores starve, the predators collapse. It's a disruption of the entire global food web.
Especially when you consider phytoplankton in the oceans.
Oh, right.
They produce half the oxygen we breathe and form the base of the marine food web. And where do they live? They live in the very upper layers of the ocean, exactly where the increased UV radiation strikes hardest.
That is terrifying.
But the fourth point in the source is perhaps the most staggering in its sheer human implications. It says, it can change the wind patterns, resulting in climatic changes all over the world. Especially Asia and Pacific will be the most affected regions, facing climate-induced migration of people crisis.
Let's just sit with that terminology for a second. Climate-induced migration. We're no longer talking about localized health hazards or struggling agriculture. We are talking about millions of human beings being physically forced to abandon their ancestral homes.
Exactly. Entire coastal regions, low-lying islands in the Pacific, and densely populated agricultural deltas in Asia becoming completely uninhabitable due to shifting monsoon patterns, extreme drought, or rising sea levels exacerbated by these broader climatic shifts.
We went from wanting colder refrigerators in 1970 to shifting entire human populations across the Pacific Ocean 50 years later. The scale of causality is horrifying. A chlorine atom plays musical chairs with an ozone molecule, and decades later, a family has to abandon an island that is sinking beneath the waves.
It really illustrates the extreme sensitivity of the Earth's systems. There are no isolated actions in atmospheric chemistry. And this actually leads us to another set of chemical battles. Because while CFCs were busy destroying the roof of our atmosphere and letting dangerous radiation in, other pollutants have been busy altering the very air we breathe down in the lobby, basically turning the rain itself into a hazard.
Right, because while the stratosphere is dealing with the ozone hole, the troposphere is choking on a completely different set of molecules. The source text provides a concept diagram that categorizes air pollutants into oxides of carbon, oxides of sulfur, and oxides of nitrogen. And it's careful to split the sources into two buckets: natural activities and human activities.
And that is a vital distinction. Pollution is not a purely modern human invention. The text notes that natural sources include volcanic eruptions, forest fires, and the decomposition of organic matter. I mean, the Earth has been off-gassing these chemicals for billions of years. Volcanoes belch massive amounts of sulfur dioxide. Swamps release methane and carbon dioxide naturally.
But the natural systems evolved to handle that baseline, right? The carbon sinks like the oceans and the forests could absorb the natural output. It's the human sources listed in the text that completely overwhelm the system's ability to process it. The text lists them. Source of air pollutants because of human activities are burning of fossil fuel and combustion engines of automobiles, kilns of industries, open air fires, and forest fires.
Right. If modern civilization wants to move fast, build tall structures, or stay warm, we fundamentally rely on combustion. We burn things. And burning fossil fuels releases staggering, highly concentrated quantities of these specific oxides. Let's examine the oxides of carbon first, specifically carbon dioxide or CO2.
We mentioned earlier that CO2 naturally makes up just 0.03% of the atmosphere, which is a tiny fraction.
It is, but its physical geometry makes it incredibly potent. The text states, CO2 forms a layer around Earth that absorbs the infrared radiations emitted by Earth's surface. Thus, heating up the atmosphere is called greenhouse effect.
This is a really fascinating contrast to the CFCs we just talked about. CFCs destroy ozone, which basically opens the window and lets dangerous UV radiation in. But CO2 doesn't block incoming UV light at all, does it?
No, it doesn't. It is completely transparent to shortwave, high-energy UV and visible light from the sun. The solar energy passes right through the CO2 molecules like they aren't even there, hits the surface of the Earth, and warms the ground.
Okay.
The Earth then naturally tries to radiate that thermal energy back out into deep space to maintain a temperature balance, but it radiates it as long-wave, lower-energy infrared radiation, just basic heat.
And this is where the molecular structure of CO2 becomes a trap. Why does CO2 completely ignore visible light but suddenly catch the heat?
It comes down to molecular resonance again. The physical shape of the CO2 molecule, which is a carbon atom with an oxygen atom on either side, has very specific vibrational frequencies. The long-wave infrared radiation radiating up from the Earth happens to perfectly match the resonant frequency of the bonds in the CO2 molecule.
Ah, I see.
So when the infrared wave hits the CO2, the molecule absorbs the energy and starts vibrating rapidly. It then re-radiates that heat in all directions, including right back down toward the surface.
It operates like a one-way mirror for thermal energy. The sun's energy gets in easily, but the Earth's heat is trapped. CFCs let the fire in, but CO2 closes the chimney. The heat cannot escape, which leads directly to global warming, which feeds right back into the climate migration crises we just outlined.
Exactly. And alongside CO2, combustion engines also produce carbon monoxide, or CO. The text is incredibly brief but definitive on this. It says, CO is highly poisonous gas, so it is health hazard.
Unlike CO2, which, suffocates the planet slowly over centuries by trapping heat, carbon monoxide suffocates the individual directly and immediately. Its molecular shape allows it to bind to the hemoglobin in our red blood cells hundreds of times more aggressively than oxygen does. If you breathe it in, it essentially locks up your blood's ability to carry oxygen. You suffocate from the inside out, even if you are actively taking deep breaths.
Yeah, it is a localized biological poison. But the text then moves on to pollutants that have vast systemic environmental impacts, which are the oxides of sulfur and nitrogen, SO2 and NOx. These are the primary architects of acid rain.
The source explains that sulfur dioxide is a health hazard on its own, but its most widespread devastation happens when it interacts with the weather. It says it forms sulfuric acid by combining with water vapors in air. Stop right there because this is where a lot of people get lost. How does a dry, invisible gas coming out of a coal power plant smokestack physically turn into a liquid acid falling from the sky?
So the sulfur dioxide gas, the SO2, drifts up into the troposphere and encounters water vapor, H2O, in the clouds. But it doesn't just mix like, say, salt and water. It undergoes a complete chemical transformation.
Right.
The SO2 interacts with hydroxyl radicals in the atmosphere, eventually oxidizing into sulfur trioxide, which then readily reacts with the water molecules to synthesize entirely new compounds. The text specifically names them H2SO4, which is sulfuric acid, and HNO3, nitric acid.
So the gas structurally binds with the water. The clouds themselves literally become vats of dilute acid.
Exactly. When those clouds condense and rain falls, it isn't just pure water anymore. It is an acidic solution. And the text provides a specific numerical value that highlights the severity of this. It says acid rain consists of H2SO4 and HNO3 that reduces the pH of rainwater to 4.
Okay, for context, neutral pure water is a 7 on the pH scale. Normal rain is slightly acidic, usually around 5.6, because it naturally dissolves a little bit of ambient CO2 as it falls. But a pH of 4 is deeply concerning. The pH scale is logarithmic, meaning every whole number drop is a 10-fold increase in acidity.
Right. So dropping from a natural 5.6 down to a 4 means the rain falling from the sky is nearly 40 times more acidic than natural rain. It is chemically roughly equivalent to tomato juice or heavily diluted vinegar raining over hundreds of square miles.
So if you are walking outside in a city and a thunderstorm rolls in with a pH of 4, you aren't going to feel your skin burning like you're in some science fiction horror movie.
Oh, no.
But what is that dilute acid doing to the environment over time?
The slow, grinding destruction is immense. The concept diagram in our source text outlines the effects clearly. First, it simply damages buildings. Acid rain chemically reacts with the calcium carbonate found in limestone and marble.
Wow.
It literally dissolves the physical infrastructure of our cities over decades. Intricate stone statues lose their faces. The facades of historical buildings slowly crumble into dust.
It is basically melting the architecture of human civilization. But the biological damage is far worse. The text includes a test yourself section, and there is a very poignant, almost tragic question written there. It asks simply, Why are plants dying day by day? Comment.
Yeah, and if we look at the effects listed in the text, it provides the answer. It's not just the acid physically burning the outer wax off the leaves, though it does that, stripping the foliage of its protection.
Right.
The true devastation happens underground. The text notes that acid rain increases soil acidity.
When the acid rain soaks into the dirt, it fundamentally alters the chemical matrix of the soil. It chemically leaches away essential base nutrients like magnesium and calcium, literally washing them out of the reach of the plant's root systems. The plants are starving to death in the dirt.
But the acid rain does something far more insidious than just washing away nutrients. It weaponizes the soil itself. The text states, heavy metals are toxic to human as well as aquatic life.
Okay, but how does acid rain relate to heavy metals?
In normal, pH-neutral soil, heavy metals like aluminum are bound tightly to soil particles. They are chemically locked away, inert, and totally harmless to the surrounding biology. But the acid rain acts as a chemical key.
It unlocks them.
Exactly. The increased acidity breaks those molecular bonds, freeing the toxic aluminum ions, allowing them to dissolve completely into the water runoff.
So this toxic soup of freshly liberated heavy metals gets washed by the rain out of the soil and flushed straight into our rivers and lakes.
And once it enters the aquatic ecosystem, it wreaks absolute havoc. The dissolved aluminum fundamentally disrupts the osmoregulation of aquatic life. In fish, it causes the gills to produce a thick, sticky mucus, literally suffocating the fish as they swim in the water.
That is horrific.
And the acid itself prevents the eggs of frogs and sensitive insects from even hatching.
It creates these haunting environments. Like, entire lakes can appear beautifully crystalline clear, completely transparent down to the bottom, but they are entirely dead devoid of any phytoplankton, insects, or fish. Just a sterile, acidic tomb. We're slowly dissolving both the physical infrastructure of our cities and the biological infrastructure of our ecosystems with every rainfall.
Which brings us face to face with the massive modern dilemma. We see the damage. We know that industrial processes, power generation, and the sheer accumulation of human waste are the sources of these atmospheric saboteurs.
Right.
And we can't just let millions of tons of solid municipal and industrial waste pile up endlessly on the ground. So humans attempt to manage it using technology to basically reduce the physical volume. The source text details two radically different physical processes for dealing with matter: incineration and filtration.
Let's examine incineration first, because it feels like the ultimate brute force approach to waste management. The text defines it clearly. Incineration is a waste treatment process that involves the burning of solid waste at high temperatures, between 650 degrees C to 1100 degrees C in incinerators.
1100 degrees Celsius is literally the temperature of flowing basaltic lava. We are constructing industrial localized volcanoes specifically to blast our garbage out of existence.
Yeah.
And from a purely volumetric standpoint, it is highly effective. The source notes, incinerators reduce the solid mass of the original waste by 80–85%.
Which, if a city is running out of landfill space, throwing 100 tons of raw garbage into a furnace and only having 15 tons of ash left over to bury seems like a massive logistical victory. You've shrunk the physical footprint of the problem.
But the laws of physics are uncompromising. The law of conservation of mass dictates that matter cannot be created or destroyed. The atoms making up that 100 tons of garbage do not disappear. They are simply forced by the extreme heat to break their bonds and violently rearrange themselves.
Right, they have to go somewhere.
Exactly, and they rearrange into highly dangerous, volatile molecules. The text outlines the brutal irony of this process. Although the volume of solid waste is reduced effectively by incineration, it produces highly poisonous gases and toxic ash.
The text lists the specific flue gases produced by this volcanic heat: dioxins, furans, sulfur dioxide, carbon monoxide, hydrochloric acid, and a large amount of particulate matter.
Let's look really closely at that chemical inventory. Sulfur dioxide, carbon monoxide. Those are the exact same oxides we just spent 20 minutes discussing, the prime architects of acid rain, global warming, and direct health hazards.
So by trying to solve our solid waste problem on the ground, we are intentionally feeding the atmospheric crisis in the sky. We are piping the precise chemical ingredients for acid rain directly back into the troposphere. We aren't actually treating the waste, we're just changing its state from a solid pile of trash into an invisible toxic gas.
And we are synthesizing new terrors in the process. The intense, chaotic heat of incineration chemically bonds chlorine and organic compounds found in everyday trash to create dioxins and furans.
What are those?
These are some of the most toxic, persistent synthetic chemicals ever studied by science, known to cause severe developmental, immunological, and reproductive problems even at trace levels. We are aerosolizing our toxicity in exchange for saving landfill space.
It feels incredibly primitive, just blasting the problem with 1100-degree heat and hoping the vastness of the sky can absorb the consequences. But the text doesn't just leave us with incineration. It introduces a completely different, highly controlled method of dealing with mixtures, listed under the skills section, filtration.
Yes.
Wait, doesn't the text offer a more elegant solution than just burning everything? Why are we suddenly talking about a laboratory scale right after municipal waste management?
Because filtration serves as a profound conceptual counterpoint to incineration. Incineration relies on chemical transmutation through extreme thermal violence. Filtration, on the other hand, relies on mechanical separation through physical structure. The text describes it as the separation of insoluble solid particles, sand, clay, dust, or precipitates, from a liquid. It is carried out by filtering a mixture.
And the physical instructions provided in the text are remarkably precise, almost artisanal compared to throwing trash in a furnace. It says a filter paper is first folded halfway, then another fold is made, so that a filter paper gets 4 folds. This folded filter paper is placed in a filter funnel in such a way that on one side there are 3 layers and on the other side there is 1 layer.
It relies entirely on physical architecture, the microscopic pores of the carefully folded paper to do the work. The text continues. The mixture is poured into the filter paper. Filtrate passes through the filter paper and is collected in a conical flask. The solid particles, residue, deposit on the filter paper.
It's like a beautifully choreographed mechanical dance. You fold the paper exactly so. You pour the mixture gently. The residue is trapped by the physical barrier. The pure filtrate flows through just by gravity alone. It doesn't require extreme heat. It doesn't fundamentally alter the chemical state of the materials. It just elegantly separates them.
Now, practically speaking, you cannot filter a mountain of municipal solid waste through a giant paper cone. Filtration obviously has limits. It only works for specific types of liquid and solid mixtures. But intellectually, comparing the chaos of incineration to the precision of filtration raises an important question regarding how modern society defines waste treatment.
Are we genuinely treating our waste, or are we engaged in a massive planetary-scale shell game? With incineration, we take a solid pollutant that is visually offensive and takes up land, and we basically convert it into a gaseous pollutant that is invisible but spreads across the entire globe. We trade a local, contained solid problem for an uncontainable global atmospheric problem.
Filtration, by contrast, actually separates and isolates the contaminant without changing its phase into something harder to capture. It really highlights the desperate need for industrial processes that genuinely neutralize or sequester waste, rather than simply converting it from a solid into a toxic gas and relying on the sky to dilute it.
Because, as we've learned today, the sky is not an infinite void capable of endless dilution. It is a highly sensitive, delicately balanced chemical machine. And that machine is intimately connected to everything happening on the surface. We are cleaning up our backyards by dumping our garbage into our own respiratory system and radiation shield.
The connections we've traced through these textbook pages today are immense and, well, incredibly sobering.
It really has been a massive journey. I mean, we started 120 kilometers up at the very edge of the thermosphere, looking at a single oxygen atom being split by a solar photon, hunting for a partner to build a fragile, 5-kilometer-thick, invisible shield. We rode the elevator down into the secure server room of the stratosphere, watching human-engineered CFC molecules act like frantic thieves, violently tearing that ozone shield apart atom by atom, letting the sun's radiation just pour in.
And we saw the biological reality of that broken shield. We saw how that radiation shatters human DNA, causing skin cancer, fundamentally alters global wind patterns, disrupts the base of the food chain by stunting phytoplankton, and could potentially force millions of human beings to migrate away from regions in Asia and the Pacific.
And then we came back down into the chaotic lobby of the troposphere and saw how our daily desire for convenience, our combustion engines, our industrial incinerators are pumping out millions of tons of oxides. CO2 acting as a one-way mirror, trapping the Earth's heat and building a planetary greenhouse. Sulfur dioxide chemically binding with water vapor to rain diluted battery acid down on our forests, starving plants, dissolving the calcium carbonate of our architecture, and leaching toxic heavy metals into our lakes to literally suffocate the aquatic life. We map this entire interconnected planetary crisis all the way down to the stark contrast of a piece of folded filter paper in a laboratory funnel.
The overarching narrative of these scientific sources is that Earth's natural equilibrium is in a constant dynamic state of reacting to the chemical inputs we introduce. The system is always seeking a new balance, but the sheer volume and artificial nature of our chemical inputs are forcing that balance to shift into states that are deeply hostile to our own biological survival.
Before we wrap up this deep dive, there's one final categorization from the source material that has been rattling around in my head, and I really want to put it out there for you, the listener, to just mull over.
Oh, what stood out to you?
The text lists the sources of air pollutants, and it places human activities burning fossil fuels in internal combustion engines, industrial kilns, open fires, right alongside massive natural phenomena like decomposing organic matter and specifically volcanic eruptions.
It does. It presents them side by side as primary equivalent drivers of atmospheric change.
If our mundane daily activities, commuting to work, using our air conditioners, burning our trash and municipal incinerators, are collectively pumping out chemical compounds that alter the atmosphere with the exact same chemical force, mechanism, and magnitude as an exploding volcano, have we as a species essentially become a continuous global geological event?
That concept cuts to the very heart of what scientists call the Anthropocene. We are no longer just living on the Earth, subject to its whims. We are operating as a primary force of nature, physically and chemically reshaping the architecture of the planet day by day, molecule by molecule.
We are a slow-motion eruption happening every single second, entirely driven by our desire for comfort and convenience. It really makes you look at a car's exhaust pipe or the humming coils on the back of an old refrigerator very differently.
The invisible chemistry that governs our lives is suddenly glaringly visible.
Next time you step outside and look up at the blue sky, remember that it isn't an empty room. It's a bustling lobby, a secure server room, and a frantically self-healing shield. And right now, the chemical diagnostics are showing us some incredibly jagged lines in that structure. Thank you for joining us on this deep dive into the architecture of our atmosphere. We hope you look up at the sky a little differently today.